Hello, my name is Christina Neilson, and this is my Physics 2211 Lab 3 over black holes and orbits. To start, part 1 of our lab was about a star orbiting a black hole. We used a computational model to analyze a star's motion to estimate the mass of the black hole. For part 2, it was the spaceship's fancy orbit around a planet and its moon. Again, we used a computational model to determine the initial velocity required to orbit around the planet and the moon without crashing. The purpose of this lab was to use Newton's second law to determine the mass of a black hole and simulate orbit. We will see later that a perfect orbit was not achievable for my model, and that the average mass of the black hole was 1.419 times 10 to the 34 kilograms, and the initial velocity used was minus 20,484 after trial and error. Some fundamental physical principles that we used throughout our computational model were the velocity update and position update formulas, the momentum principle, Newton's second law and momentum, and the universal gravitation formula. For part 1 of our lab, here is the initial part of our glow script code where we lay out our initial conditions. Delta T is 1 Earth day in seconds, which is 86,400. Our system here is the star, and our surroundings are the black hole. Here's more of our glow script code from part 1. We have the momentum principle at the top, Newton's second law, the parallel component of the net force, and the perpendicular component of the net force all laid out in this code. We also rearranged the universal gravitational formula to find the mass of the black hole, which is big M. Here's the results of our glow script code. We can see a perfect orbit, and our average mass of the black hole was 1.419 times 10 to the 34 kilograms. For the second part of this lab, we also again laid out our initial conditions, and I increased my time to run simulation here in order to see an orbit of the moon. Our system was a spaceship, and our surroundings were the planet and its moon. Here's more of our glow script code. We use the universal gravitational force equation and the velocity and position update formulas. Here's a result of my code. We can see a full orbit of the moon around the planet. However, we do not see a fancy orbit of the spaceship, which should be the magenta line. Instead, we just see a straight line. Our initial velocity that we used to get this perfect orbit of the moon was minus 20,484. Some possible sources of error. The mass is a computational prediction, so it is possible that it did not align with real life. I used a trial and error method to determine the runtime and initial velocity, so it is possible that a better set of numbers exists, or doesn't, that would have produced a better orbit. Now for some questions. What does it mean? How do the parallel and perpendicular components of the net force differ from the parallel and perpendicular components of the change in momentum? The net force is the sum of all vector forces acting upon an object. And the rate of change of momentum is a result of the net force, but it simply measures how an object's motion changes over time. The perpendicular component of the net force changes an object's direction, while the parallel component changes an object's speed. A second question. What if this imaginary system has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interactions in the system. Would there be any dominant interactions, or would they all contribute more or less equally? To compute this, we would actually need to calculate the gravitational force of each object now in our system on all other objects in the system. Then, after all of that, we would need to find the net force acting upon each object. Because the mass of the black hole is the largest, its gravitational interactions would be the dominant ones here. Thank you.